Today we want to spend a little bit more time on the qualitative implications of impulse. Okay, we know all about the math. The math is easy for us now. Okay, I think we did a pretty good job on the quiz that we just wrote. But what does it mean qualitatively? What are some of the deeper meanings behind impulse beyond the mathematics? Well, let's go back to the equation for a second. The basic equation, as it appears on your data sheet, is F times delta T is equal to M times delta V. I want to focus on the first part. F times delta T. So let's say delta P is equal to F times delta T. There are two important implications that come from this equation, qualitative implications that come from this quantitative equation. The first, we talked about this a little bit, we just haven't written anything down about it. The first is when we have what I call a predetermined impulse. And we have a predetermined impulse typically when you're stopping an object. The car is coming to a stop, whether it be at a stop sign or crashing into another car. The ball is coming to a stop, whether it's being hit by a baseball bat, whether it's being caught by somebody with a baseball glove, or whether it just falls on the ground. The ball is coming to a stop. Okay? Whatever comes to a stop has its impulse predetermined. It's determined simply by its mass and how fast it was moving before it began to stop. Car traveling down the road at 100 kilometers per hour. It has a certain amount of momentum. When it's stopped, it'll have zero momentum. The impulse or the change in momentum will be the same no matter how it stops. It's a predetermined impulse. The second implication is when we don't have a predetermined impulse. I don't know if this is a word. I don't even know if you can do this or not, but this is an English class, right? Let's call it a non-predetermined. Can you have two hyphens in a word? I don't think so. But you know what I mean. An impulse that is not determined by the initial conditions of the object. For instance, a golf ball is sitting on a tee. You're going to hit it. The impulse that the golf ball experiences when you hit it is not predetermined. If you hit it harder, it'll go faster. The impulse is greater if you hit it harder, right? Typically, a non-predetermined impulse comes when you're starting an object. A golf ball that's sitting on the ground, a baseball that you're going to throw. When you're causing an object to speed up is when we have a non-predetermined impulse. So what are really the implications of both of these situations when we have a predetermined impulse or when we have that non-predetermined impulse? Well, when you have a predetermined impulse, if you take a look at that equation again for a second, if this number doesn't change, if that impulse is the same no matter what, and we increase the time that it takes to stop the object, if we increase the time interval, then the force must go down. And this is what we based our activity on yesterday, right? Our egg drop activity. If we increase the stopping time, then the force must go down. Just a couple quick little numbers. Hey, the impulse is 10. Time is 1. The force must be 10. If the impulse is 10, and it is, it's got to be the same because it's predetermined. But I double the stopping time to 2, what happens to the force? 5. If the impulse is predetermined and you increase the stopping time, the force must go down. And that is either the basic principle or one of the two basic principles behind every impact cushioning device, period. Everything that cushions an impact increases the stopping time to decrease the force. Now, some things have another principle involved as well. We talk about a hockey helmet. Well, a hockey helmet increases the stopping time, decreases the force by the foam inside the hockey helmet. But what it also does is spreads that force over a bigger area. So that force isn't being absorbed by one spot on your head. Rather, it's being absorbed by your entire head. Okay? That's not what we want to look at right now. Okay? That's certainly a part of a lot of impact cushioning things out there. Okay, but the part of it that we want to look at, the part that's always there, is the idea of increasing the stopping time, decreasing the force. Catch a basketball. How do you catch a basketball? Not like this. Okay, you cradle the basketball, right, as you're catching it. I'm exaggerating it right now. Okay, but you know, everybody, even whether you play basketball or not, you know you're going to cradle the ball a little bit, right? Okay, you catch a baseball, same thing. Even take a pass. Okay, with in hockey. Okay, you cradle that a little bit. You don't just have your stick rigid, waiting for the pass to come because it's going to bounce right off, right? Stopping time is too small. Force is going to be too big. Not going to stop the puck. Going to stop it, but it might bounce right off. Even soccer. Okay, I'm not a soccer player, but I'm sure in soccer you're cradling the ball a little bit as you're taking a hard pass. Okay, every goalie pads, right? Everything that's designed to take an impact has to increase the stopping time to decrease the force. Make sense? Now I'm going to give you the second one, then I'm going to show you a couple videos. I'm going to ask you to tell me which situation is explained in which video. The second one is when we have a non-predetermined impulse. This is when we're starting an object or trying to speed up an object. The impulse is still equal to F times delta T. But this time, delta P is not a constant value. It can go up or down. It can be a bigger value or a smaller value. Who's a golfer here? Okay. How many people have never golfed? Okay. Most people have golfed at some point. Might not be very good. I'm not very good, but I golf a little bit. I know that part of hitting a golf ball 300 yards, which I can't do, by the way, is how hard you hit it. I know that the stronger you are, the more you're going to hit the golf ball. But I also know that it's not just based on strength. If it was, then the strongest people in the world would be the best golfers in the world, and they're not. What's it all based on? What's it also based on? And probably more than strength, in fact. Based on technique, right? How you hit the ball. When you hit a golf ball, you don't do this and just stop the club head when it hits the ball. What do you do? What do you do when you hit a golf ball? Or even hit a baseball? Or take a slap shot. Follow through, right? Follow through. What does following through do? It increases the time of contact. Now, if you increase the time of contact, an impulse is not predetermined, then you're going to increase the impulse. The ball's going to go faster. The other thing you can do, besides having better form and having the ball in contact with the club or the bat or the stick for longer, is increase the force. If you hit it harder, the impulse will get bigger. So two factors here. The increase force, increase time, impulse gets bigger. Okay, again, in the first situation, if we increase time, it affects force. In the second situation, if we increase time, it affects impulse. If we increase force, it also affects impulse. Does that make sense? All right, I'm going to show you a couple videos right now, and I want you to tell me which video, not the videos that you actually see written there, or at least one of them is not. I want you to tell me which one is which, okay, to see if you really understand what I just said. All right, so we got an understanding now after those videos, I think, of these two implications of impulse. We will see these on a test, I promise you. It might not be the Cirque du Soleil guy landing on the mat, okay? It might not be Phil Kessel taking a wrist shot like you saw in the video, okay? It might not be anything that you've seen to this point. But if you're trying to start an object or trying to stop an object, it's related to this. If you're cushioning an impact in particular, it's this is the one that you see the most often, right? This is the one that you see the most often when you're trying to cushion an impact of something. You be prepared for that. Okay, one final little thing here, and then we'll wrap it up and drop our eggs from yesterday here, okay? The first graph of the year that we're going to see is a graph that describes impulse. The graph is going to be a force versus time graph. Force on the y-axis, time on the x-axis. Typically, that graph will involve straight lines. Not necessarily one straight line like this, Might be a couple straight lines or 3 or 4 straight lines, but typically it's going to be straight lines so that you don't have to worry about any kind of tangent lines or anything like that. We can find from this graph the impulse. In fact, I'm going to ask you a question tomorrow. The question that I'm going to ask you tomorrow is, what's the first thing you think of when you see a force versus time graph? The answer to that question from all of you is going to be 3 words. Area equals impulse. Okay, those are the 3 words I want to hear tomorrow when I say, what do you think of when you see a force versus time graph? You're going to say area equals impulse. Now, you will always find the area of an F versus T graph. I don't even care if you're asked for impulse. Okay? You're going to get it anyways. You may have to do something else with it. But the first thing you're going to do is get the area, which is the impulse. And then, if we have to, we'll go from there. Now, I said that you're always going to do area equals impulse, but I also said that you might actually be looking for something besides impulse. I don't care. You're still going to find area equals impulse. But then you might have to do something else. Well, that something else is often the change in velocity. Once you've got the impulse, which is the area, you might end up using m times delta v in order to find the change in velocity. What you won't use on one of these graphs is this. You won't use f times delta t. We'll get a graph for a second. Even the most simplistic f versus t graph. Why could you not use f times delta t here? Yep. No, the graph, force versus time graph, would still give you impulse. It's not the impulse part of it that's the problem. It's the force part of it that's the problem. What force do I use? This. What force do I use? It's a changing force, right? So I can't do it. This accounts for a changing velocity. This doesn't account for a changing force. So this is a perfectly valid equation if your force is constant. But if you're dealing with a changing force like that, let's not go there. Okay? Okay, one quick example here, and then we'll wrap it up. Drop our ice here, okay? It says, golfer hits a long drive, sending a 45.9 gram golf ball. Hey, you're going to take your ugly colored highlighter right now, or your red pen, and circle that because we don't want grams. Shows an approximation of the net force as a function of time for the collision between the golf ball and the golf club. We want to find the impulse and the velocity after they separate. This is kind of an odd graph here. Oh, one more thing I noticed here, actually. Milliseconds. I want to circle that or highlight that as well. It's kind of an odd shape here, right? The force is increasing, then it reaches a peak value, then it decreases. Is that realistic? Sure it is. When you hit a golf ball with a golf club, the force increases as the golf ball compresses more, right? It's Hooke's law. Right? As there's more squishing, the force gets bigger. But then the ball goes back to its regular shape. And what happens at that point? Well, the club's still in contact with the ball, so there's still a force, but the force is now decreasing. So the force increases and then decreases, all the while still imparting impulse. What's the first thing you think of when you see this graph? 3 words, come on. Area equals impulse. So I don't care what you're asked for. Let's do area equals impulse. Let's get the area here. It's a triangle. So it's going to be 1/2 base times height. The base of it goes from 0.1 to 1.1. So it's 1.0 times 10 to the minus 3 seconds. I remember doing that because I circled milliseconds, or I highlighted it with my ugly highlighter, whichever. My height here is 5,000 newtons. When I do the math there, I think it works out to be 2.5 newton seconds or kilograms meters per second. What's the velocity of the golf ball? At the moment the ball and the club separate, well, first understand that the golf ball was at rest. VI is 0. So VF will be whatever delta V is, right? Whatever the change in velocity is. How am I going to do this? Well, I know what delta P is already. Let's set that equal to M times delta V. Hey, by the way, tell me where here. I'm going to trace this through. Tell me to stop wherever the golf ball and the club separate. Tell me to stop where they separate. Stop right there? Did they separate there? No. Think about that. If they separate right there, how is the golf club applying a force on the ball right here? Right? It's a smaller force than it was right there, but it's still a force. The golf club can't apply a force on the ball when they're still in contact. Where do they separate? That's where the force is 0, right? That's when the club is no longer touching the ball. That's what we found the impulse for. Perfect. We know the impulse is 2.5 Newton seconds for the entire time of contact. The mass of the golf ball is 0.0459 kilograms. Delta V, solve for it. 2.5 divided by 0.0459. What is that? 54.46. So we'll go 54.5 meters per second. Is that good, guys? What if we hadn't even been asked for A? What would be the first thing you would think of when you see this graph, even if you're not asked for A? Still 3 words, area equals impulse, because you still had to find the area to get question B, even if you weren't asked for the impulse. Got it? Here's your homework. Oh, you guys are all packing up your books thinking you're going to get away without any homework here. Here's your homework. Let's go page 462, the practice problems. And let's also finish up question number 9 on worksheet number 2. Worksheet number 2 is the one you've already done, but I told you not to do question number 9 because it involves this graph. So 2 questions on 462, and then question number 9 on worksheet number 2. All right, that's it.